Alright, hi everybody, welcome to the Chapter 6 lectures. I'm going to try and separate this into two videos so that you can watch them separately. Probably keep them to less than 10 minutes each just to make sure you can get through them in a timely manner. So chapter 6 is going to talk about the electronic structure of atoms, and we've talked about this before in classes, and you've seen this stuff before. The first thing that we want to really discuss is just exactly how light can move, and in talking about that, we're going to talk about the wave nature of light. And so what this means is that light is treated as both a particle and a wave. Fancy terminology for how light is very difficult to actually track when it comes to its movement. So the first way we're going to treat it is as if it is a wave. So if you think of a wave, like of course on the ocean, we can measure a few different things about it. One of the things we can look at is how far apart the peaks of the waves are, and that's where you see the wavelength here on your screen. Other things we can look at are troughs, so the bottom part of our waves, and peaks, which are the top part of our waves. Another thing we can talk about are actually amplitudes, and that's going to be the distance from, say, a line. If you tried to draw it straight through our waves and it was kind of like equal above and equal below, then we would see that the amplitude is the distance, the furthest distance from that equilibrium line, if you will, that the top or the bottom of the wave gets to go to. Those of you that have already taken pre-cal, we also like to simplify our waves into what we would call functions, like sine functions. So if you graph the sine function, you'll actually see that it's a perfect wave, and that's one of the most common ways of describing this. This is all leading us into talking about types of electromagnetic radiation, really just the one type of electromagnetic radiation, because we want to end up having a discussion about energy. Yeah, we've already talked about energy in the form of heat, but another form of energy we want to discuss is going to be light based. And that's because a lot of reactions, when they react, actually produce that light. So we want to be able to analyze that light that comes off based on a couple of different factors. Another thing that we can describe waves with, again, sine function. If you look at A, it looks like a sine function. B does too, but the waves are closer together. And that's because the frequency of the first wave is going to be smaller than the frequency of the second wave. So the longer the wavelength, the smaller the frequency. The shorter the wavelength, the higher the frequency. And frequency has to do with, if we put like a post right here and we dragged our waves across it, pulling at about 1 wave a second, we would see that a certain number of the peaks of the waves would travel across that post in a certain set amount of time. And what we're looking at is if we take that same amount of time and we pull this guy down here, what we're going to see is more of the peaks. In fact, 1, 2, 3 of them will pass in the time it takes 2 up here to pass. And that has to do with how quickly that light is actually moving. From there, we talk about the electromagnetic radiation spectrum. So this is how all photons are actually treated. The visible region is the region where we spend a lot of our time. This accounts for everything we see with our eyes. Now, all of the electromagnetic radiation has the exact same speed. The speed of light is known as 3 × 10⁸ meters per second. That being said, we can also relate that speed of light to frequency and velocity. So if we know that the speed is always going to be this 3 × 10⁸, this is wavelength and this is our frequency. We know that wavelength times frequency equals that 3 × 10⁸. And when we look at different types of electromagnetic radiation, like for instance radio waves, they have a really, really long wavelength on the order of hundreds of meters as compared to gamma rays, which have, on the order of very, 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 very fraction of a meter, very small fraction of a meter. You will also notice that these two things tend to be inversely related. So as wavelength goes up, frequency goes down. Okay, so this is how we're going to account for that speed of light idea. You'll also notice that on here, of all of the different types of radiation, you've probably heard of almost every single one of them, if not all of them. The one you probably haven't heard much about is the gamma rays, and we'll talk a little bit about why. But gamma rays are responsible for instant DNA degradation. So these are things that we don't want to interact with gamma rays because they will break down your DNA. X-rays and rays in this particular area, UV and X-rays, are responsible also for DNA degradation, but at a much smaller level. And when it happens, it results in like mutations. So if you've ever thought about things like cancer from sun rays are going to be ultraviolet, and whether it's UVA or UVB, those ultraviolet rays are heavily linked to changes in DNA. Those changes in DNA are called mutations, and then of course later on we actually refer to those mutations as cancers. So if you're wondering where this idea of cancer and skin cancer comes from, it has to do with the DNA mutation. That's where most cancers are linked. All right, next thing is going to be on how we can talk about how the wave nature of light is not the only thing that we can use to describe light. So for instance, we can say that that light acts like particles and it moves in this wave-like manner, but that doesn't really explain every behavior of light. And remember, light is a form of energy. So one of the ways that we're going to learn how to describe this involves Max Planck's concept of quanta. And all that is instead of saying that energy is like a spectrum where things move smoothly up and down, energy is actually going to be found in packets, and we're going to call those packets quanta, specifically when we relate them back to photons, and photons of course being little packets of energy known as light. So when we talk about the difference between a person walking up this flight of stairs and walking up a ramp, the potential energy from his first step to his next step on this ramp could be very, very small, or it could be very, very large, depending on the size of his steps. With a ladder, those steps are defined already. So we're going to use this idea of the ladder of energy and call them quanta instead of just an ongoing spectrum. So then, of course, along came Einstein, and he decided, well, this is what's going to actually explain what we call the photoelectric effect, which has to do with how much energy a certain frequency of light actually contains. So he concluded that energy is going to be directly proportional to frequency. So if a thing has a lot of energy, it's going to have a high frequency. If it has a low amount of energy, it's going to have a low frequency. And that, of course, also comes along with a constant in this particular calculation. This is Planck's constant because it was, of course, named after Max Planck's quantized energy orbitals. From there, we can talk about how to combine these two things. And this is something that we've discussed in the past, but what we can look at here is we can actually describe how energy is released from an atom when energy is actually put in to that atom. So for instance, if I heat up a sample of salt, of say sodium chloride, the sodium metal is going to give off a certain color when it hits that flame. And we did this last year in honors chemistry. I believe we did this in honors chemistry 2 years ago as well. So you all got to do the flame lab. The whole idea behind the flame lab was to calculate what the frequency of light was given wavelength, and wavelength was determined from colors. And so when I'm back, we are going to go through and we are going to do the flame lab. It doesn't take very long, and it's nice to see all the different colors. So we will go through and we'll look at how this is related. But one of the things to note is that every atom gives off its own specific color, and that color is referred to as an emission spectra. So that emission spectra has to do with how much energy is actually being emitted once that sample gets heated up. Every single atom has its own characteristic set of energy packets. And so, of course, that also means that they have their own specific colors of light they give off. And we can actually use a specialized technique that allows us to get a line spectrum. And this is going to have several wavelengths that'll identify a single atom. Now, we use this as kind of like a fingerprint. So hydrogen will always have these 4 lines. Neon will always have these lines that relate back to its specific signature, if you will. So we use this as like a fingerprinting technique. And this is a really old way of identifying atoms. Now we use a technique called mass spectrometry that actually identifies atoms by mass and molecules by mass. But for now, this is just kind of something to understand. This is the basics behind how we've seen fingerprinting before when it comes to different atoms. Moving on to Niels Bohr and Planck's assumption, one of the things that we want to understand is how is this going to get us to the next concept? Because one of the things we're moving towards is identifying electrons in atoms specifically. And that means identifying their energy states. So that's these excited states. That means identifying their spin states. That means identifying what kinds of orbitals they occupy as far as the shape of those orbitals. You guys probably remember learning about s, p, d, and f orbitals, but if you don't, then we are going to go through that again. And so Niels Bohr is the guy who comes along and says, all right, electrons and atoms are more complicated than Max Planck's idea that they all move in these quantized energy states. Now, you've heard Bohr's name before, in that he came up with the Bohr model of the atom. This is a different version, but this is the exact same type of thing, where you draw a little circle in the middle, and that's where your protons and your neutrons go, and then you draw varying orbital sizes that slowly get away from the center of the atom, and those individual rings account for excited states of electrons. So one of Niels Bohr's major assumptions is that electrons can only occupy certain orbitals that correspond to certain energies. So, for instance, if an electron is going to move from the ground state to n equals 2, that electron needs to get or obtain a certain amount of energy in order to do it. And that amount of energy is going to be the same as that electron trying to move that transition 3 or 4 times, right? If there are 7 electrons trying to get from n equals 1 to n equals 2, then all 7 of those electrons have to have this exact same amount of energy to do that particular transition. So, sorry, my neighbor's dog. So that being said, if we were saying an electron wanted to move from n equals 1 up to n equals 3, a different amount of energy would be involved in that particular transition. So that's his first assumption. His next one is that if an electron is already in an orbit, that there are specific allowed energies, and those energies are not going to be released from that atom as long as the electrons are contained within a correct orbit. Okay? Our next assumption is that when we absorb or release energy, that an electron moves from one energy state to another. So for instance, if we go from n equals 1 to n equals 2, that electron is nowhere in between. It's either in n equals 1 or it's in n equals 2. It cannot be anywhere in between. It has to be in a discrete orbital. In the case of our particular energy states, we say that the energy that is going to be required is equal to Max Planck's constant times the frequency of the electron that we're looking at. That being said, we're going to say that we can actually calculate using a more complicated version of the equation for change in energy given different pieces of information, where initial and final energy levels are given by these n values. H is still the Planck's constant. C is the speed of light. There's another constant here. The change in energy is going to be specifically related using this equation to these constants and to the energy levels of the electron in 2 different states, because what you're trying to calculate is the change in energy needed to go from one orbital to another or from one orbital to another. Okay? All right, so that being said, we move on to Louis de Broglie. He's a different scientist who actually says, all right, well, it's nice to hear all of these things, but if light's going to have all of these different material properties, then matter should also have the same properties. In other words, that if light moves as a wave, that matter should also have wave-like properties. He demonstrated that this is the case by measuring mass and wavelength and describing how the two are related using Planck's constant again, and with the wavelength of light, the mass of the particle, and then the frequency. Which brings us, all of that kind of comes together to give us the uncertainty principle. And we've talked, I'm sure you've heard of the Heisenberg uncertainty principle before, but if you haven't, it's a really fun one. What he says is, based on all of the information he's gotten from all of these scientists, that the more precisely we know how quickly a particle is moving, the less precisely we know where specifically its position is located. So for instance, if an electron is moving really, really fast, and we know how fast it's moving, we know very little about where its specific location is. And so there is some kind of in-between area, but he does, in fact, prove this using a few different types of experiments, okay? All right, so I'm going to pause there, and I'm going to stop this video for now, and then I will have a part 2.